Hi everyone, I'm Katie from Hackster. Thanks for joining us today for the Concept to Prototype with Ultra96 event with Avnet and Xilinx. This is going to be a 4-hour event, and it will include demos and discussions about creating a viable automotive prototype using the Ultra96 V2 and Xilinx solutions. We'll also take the opportunity at the end of the event to answer some questions you might have along the way. So I'll kind of explain how we're going to do that in a little bit. So we've got 3 industry experts with us today: Adam Taylor, Kevin Kirk, and Nick Nee, who will be showcasing the demos and discussing how you can take your concept to prototype with Ultra96. So Adam Taylor is the author of the MicroZ Chronicles, which has been running for more than 6 years, and with more than 300 articles and 20 million views, has taught engineers how to use the Zynq NP-SoC, and Xilinx FPGAs. When he's not teaching or writing about FPGA SoC development, Adam develops FPGA-based solutions for a range of applications, including radar, nuclear reactors, satellites, cryptography, and image processing. He is also a chartered engineer, a fellow of the Institute of Engineering and Technology and a visiting professor of embedded systems at the University of Lincoln. He is also the owner of the engineering and consultancy company, Adwevo Engineering and Training. Kevin Kirk is our second speaker. He is a software engineering manager with Avnet. He is a computer engineer by degree, technical marketing manager by day, and an embedded software programming addict from an impressionable age, which has turned into a mostly healthy fascination with FPGA and other hardware craft over the past 11 years at Avnet. We also have Nick Nee from Xilinx. He is the director of product marketing for AI software and ecosystem at Xilinx. He is responsible for product planning, business development, and marketing for Xilinx's AI and software products. Prior to joining Xilinx in 2014, Nick held multiple roles in R&D and applications focusing on embedded system design, high-level synthesis at ATI, AMD, Qualcomm, and Altera. Nick has an MS in computer engineering from the University of Toronto, and he holds over 10 patents and publications. So today we're going to have Adam will start off with an introduction. He'll give you an overview of the tools and used in today's demo. We have 3 demos today, each followed by a fireside chat. There will be a break in the middle with a Q&A session at the end. So Adam will go over the schedule in the next slide here, and then I'll also try to post that in the chat so that it stays during the event and you can check that out at any point. And then to ask questions during the event, there's a Q&A section at the bottom of your screen. So you'll see a Q&A little clickable item there, so you can ask any questions in that, and we will try our best to answer them throughout the event. So Kevin's here to kind of help answer those via text. We may be able to answer some of them during the fireside chats if they are relevant to the chats, and then we'll have a 15-minute section at the very end of the event where we'll answer all those questions as well. If for some reason we don't get to your question, we're going to do our best to try to get to all of them, but time might not allow that. So if we don't get to your question, there's also the Ultra96 hardware design forum on element 14 that you can visit, and I will post the link to that as well. So that's a good place to go get your questions answered for this board and for anything that we talked about during this event. So without further ado, I'm going to let Adam take it over from here. Thanks for joining us.
Hi, how are you all doing this morning? Thanks for joining us for this session. I think it's going to be a really interesting session today. We've got some really good demonstrations lined up and some really good examples. So what we're going to do is we're going to take a look essentially through 3 elements of the design and how we can move from our initial concept, our initial ideas, to being able to move through different stages of development, working towards a final prototype. But as we move through those stages of development, we want to be demonstrating capabilities, retiring risks, and overall increasing the technology readiness level of the prototype that we're working on. And so today we're going to have 3 sessions, as Katie was just saying. So the first session we're going to look at how we can actually create this base imaging processing pipeline, and that's going to be really fundamental to everything else that we do throughout the rest of the morning. we're going to do several different changes and modifications to it in Vivado. I'm not going to be building this. I'm not going to be building this live. We're going to be building this as it's all pre-built. But we're going to start in Vivado. We're going to move through to using Vitis and to using Limit, and we will have some pink in there as well in the second section. So it's going to be a really good session. In the second session, like I said, we're going to take a look at what we can do with Ping to accelerate our applications, and we will also try to have a good system and a break in between. I'm just seeing some questions on the audio, so I'm just going to mute myself. I'm just going to check my audio settings and just make sure that they are as good as can be. So hopefully they are okay, and we're seeing things through. So we'll try and move on. Obviously, we're gonna take a look at Ping. We're gonna take a look at how that works. We're gonna take a look at the creating, and then finally, once we've got our base imaging platform created in Vivado that we're going to demonstrate in page 1. In session 2, we're going to look at how we can prototype our algorithms and make our algorithms really simple and get going with our algorithm development. And then in the final stage, we're going to look at what we need to do to wrap it all together and pull it all together. Now, I see somebody's already asked a question about what material will be available after the event. So as of this morning, I've released all 3. There are 3 Hackster projects which detail each one of these 3 sections. And I'll give you links at the end of it to all these designs, all these Petal Linux board support packages, and all of the Vitis acceleration package platforms that have been created to get us working and to get us going there. So we'll be providing that at the end. First, I want to talk a little bit about what our concept is. So our prototype concept and our actual overall vision. So it's not unusual in many applications to be asked to be able to create a prototype and to go away and take a look at what equipment you've got, what development boards you've got, what's easily accessible sensors and cameras you've got, to go away and be able to create something. And in this instance, we've been asked, we set ourselves a challenge. We've been asked to create a flexible autonomous embedded vision system. And what we really mean by that is we want an embedded vision system that can work with at least 1 camera, but scale to have multiple cameras. We want it to be able to have the capabilities to be able to enable higher levels of the SAE autonomous driving solutions. So levels 4 and levels 5 of the driving capability. So we want to be able to ensure that people can address those as well. We want to have we want to work with a good quality camera, because obviously we're going to be using this for safety critical applications, for navigation. And we need essentially to be able to use this for a wide range of applications. So we want to have a good resolution. So we're going to have a 720p resolution at least, and at least 30 frames per second, so as we can have a fairly realistic real time. And what we want to do is we want to leave our system such that it is expansible, and we can easily then, once we've created our system, we can take this system and go away and create AI and machine learning applications on top of this image processing system that we have created. So our objective for this prototype is what I was just really talking about a little while ago. And we want to create this prototype using COTS components. You know, we don't want to go away and start investing significant amounts of money in obviously custom board designs and so on before we know whether it's actually feasibly possible with our idea of an approach. We want to create a solution that gives us really that real easy ability to implement algorithms. So we want to be able to easily implement the algorithms, easily manipulate and modify the algorithms, particularly as we'll be working with the real world sensor. So we'll not be working with videos in OpenCV on a computer desktop, which is the best case. We'll be working with the real world sensor running on the target with the real world sensor limitations in terms of image noise, performance in low light and high contrast situations. So we want to be able to test that in our image processing application. And what we want to do in all of our applications is really we want to be able to retire risk. all this is about is prototyping is about retiring risk that is contained within the project, in any project. And early on. So the first thing we want to be able to kind of retire at the risk level is, can we physically connect, all the components that we've identified for the prototype? Can we actually get those connected together, get those working, give us an image processing stream? Once we've done that, what's the next step? Can we get our algorithms running? How do our algorithms behave with the real world sensor? Then the third and final step is, how do we actually leverage the performance that we've got in the FPGA and the programmable logic that's available on this device to actually give us the best case performance? And all this is really about, as we go through this, it's really increasing the technology readiness level, and that allows us to demonstrate to our stakeholders, maybe their internal project management, other projects, or external stakeholders if we're looking at developing a custom application and we're looking for external funding. All this is about is being able to increase that technology level so that we are taken more seriously by our internal and external stakeholders. Now, our journey today, as I mentioned, is going to be quite an interesting one. We're going to start out creating a fairly simple image processing platform using Vivado and Vitas in the embedded flow. So we're going to do that just to do that, proving that I was just talking about, that the hardware that we've selected will come together and give us the basics that we want, that we can pass an image through it and display an image. Then we're going to take a look. We're going to throw a pink. We're going to use pink because we can easily use the algorithm, the Vivado design that we've just created. We can pull that into pink and use that as a pink overlay, and we can then really simply start using Jupyter notebooks, OpenCV, all the power of Python that we have to be able to test our algorithms, to work on our algorithms with that real world sensor. Once we've got our algorithms and our real world sensor complete, we're going to move across into looking at Vitas, and we're going to use the Vitas acceleration capability. So its ability to use OpenCL to accelerate functions from running in the PS to be running in the programmable logic. And by this point we'll have identified algorithms that we want to move across, and we will be able to then move those algorithms across into the programmable logic and get the best performance possible from the overall system. It sounds really simple when you say it fast, over a few minutes. It's taken me a good month or 6 weeks to actually create all these demos, to create all this material for this. So I hope you're really going to enjoy it. And actually, at the end of it, I'm passing across a lot of base information as well, base platforms, that you can take and you can use in your own developments. So what we're going to use today to get started. So we've got a relatively straightforward, really low-cost BOM. This is just exactly what do we need to be doing to get going with this. So we're going to have the Ultra96 V2, as you can see there. We've got the JTAG to UART connector as well, so that allows us to access the UART and the JTAG that's on the Ultra96. We've got a MIPI adapter, so the Ultra96 obviously breaks out its high-speed connectivity from the programmable logic to the high-speed connector and some signals to the low-speed connector, and this MIPI board actually just connects into that high-speed and low-speed connector and gives the interfacing with the MIPI capabilities. And then we've got a MIPI PCAM5, which has got the image processing, the MIPI sensor on it, that we're going to configure, and we're going to grab the images from. Move on to the next slide. So let's take a little bit of a look about where we want to do image processing in automotive applications. Now, over the years, I've worked on a few image processing applications for autonomous driving and for automotive applications. And the main areas that we use these vision capabilities in are, we might want to have a surround view, which brings together all the cameras in the car to be able to fuse those together and creates a surround view of the vehicle such that the vehicle can see its surroundings. So those can be used for when it's doing, say, parking assist or low speed navigation. We might want to have forward view and rear view for doing navigation and autopilot type systems. We might want to consider safety and have blind spot detection on door mirrors and such that we can see, we can detect objects for example, motorcyclists, for example, in the blind spots, so as we can pull those through and make sure that we're not inadvertently going to make a maneuver in our car that might risk damaging or collision with something in the blind spot. Of course, as well, a big interesting thing at the moment is monitoring not only the external environment of the car, but also the internal environment of the car. And in that case, we want to be able to monitor the driver. Maybe we want to monitor the driver for drowsiness to make sure that the driver is not drowsy at all. Make sure he's paying attention and he's not there. And maybe we also want to do some occupant monitoring as well. So the reasons we might want to monitor the occupant, so we might want to later on implement some machine learning, artificial intelligence algorithms that allow us to detect movements of occupants' hands to be able to control, say, things like climate controls within the vehicle or media controls or such like. And that's increasingly popular in a number of vehicles. So I want to start really with a little bit of an introduction into the basics of image processing, just to set the scene a little bit about what we're doing and how we're going to do it and the key importance of it. Now, the really interesting thing, obviously, is that as humans, we see a very, very, very limited element of the electromagnetic spectrum. But actually, what we can do with embedded vision is if we select the right sensor, we can see really beyond the visible, we can image beyond the visible range of the human visibility. So it gives us extra awareness and extra capability. So for instance, we can look at the infrared for thermal and low light performance and night performance. We can look at X-rays and things like that, not that we might want to in an autonomous vehicle, in an automotive application, but it gives us that ability to see really across the electromagnetic spectrum. And depending upon the technology type we select, is the range of the visible spectrum that we can, the range of the spectrum that we can work with. So if we use charge coupled devices or CMOS sensors like we'd find in the image sensors that we're going to be using, we can see pretty much from the X-ray end to the visible and maybe just a little bit into the very near infrared, depending upon the manufacturing of the sensor itself. If we want to see anything thermal, then we need to move into more custom technologies, more specialist technologies, and start using things such as uncooled IR sensors, the FLIR and FLIR Lepton, or some of the larger sensors like that, or really high grade sort of cooled sensors to allow us to do that. But we've got the real key thing is here we've got a range of sensors to pick from that we can use to go across that spectrum. Now, selecting the right sensor can be a bit of a challenge as well, particularly when you're thinking about automotive applications. One of the key indicators of performance of an image processing sensor is actually the quantum efficiency. And the quantum efficiency, really, it's the number of pixels that are number of incident photons which are striking the device compared to the number of photons that we actually receive at the end of it in our pixel in the device. And what can happen with some sensors and with the sensors that you can see in the diagram there is that actually structures in sensors, as the sensors actually constructed, such as metallization layers and such that perhaps lay over the top of sections of pixels, will really have an impact on the quantum efficiency when they're implemented from the front. And that's because the photons strike these structures and they're reflected away and they move into a different pixel, or they reflect out of the image sensor itself. So that can have a real impact on the quantum efficiency and the performance of your image processing sensor. A better solution actually is to look at image sensors that actually allow the light to be incident on the back of the sensor. So all the construction, all the metallization layers there on the front, but actually you can, if they do chemical mechanical polishing of the back of the sensor, you can remove some of the silicon substrate from it, and the incident photons can come in from the back, and then you get a much better quantum efficiency because you don't have the scattering that occurs when the photons strike device structures, because there are no device structures present. Now, this is really important if you want to have good low light capability. So if you want to, which is important for automotive vehicles, because 12 hours of the day, the car could be operating at night, the embedded vision system could be operating at night. So you want to have the best low light performance possible. And an example of a sensor that does that, actually, that pulls in, that has a back back illumination, is the 233AT from onsemi, if anybody's interested in taking a look at this. Now, the other thing we do, of course, is we want to, the world is color, and we want to work with a color world, obviously, and be able to see and process our images and record our images in the color world. And that's tricky when you think about how an image sensor might do that. And how it's actually done is, in front of each pixel on the sensor, we put what's called a Bayer mask on it. And that Bayer mask only allows through one wavelength of light. So it will either allow through a wavelength of red light, green light, or blue light. And that's all that will be contained in that pixel, either the red, green, or blue spectrum of the image will be contained in that pixel. And then we will read them all, then we will read all those pixels out. But what we want to do is actually reconstruct this into actually having a color, not just the red channel, the blue channel, or the green channel, but to actually have a color there. And that's one of the things we do when we do what's called debayering, where we work through groups of pixels to actually work out what the actual color of that pixel actually is. And to do that, we work in typically a group of a 2x2 matrix. So we'll work in a typical 2x2 matrix, and we will have one red pixel, one blue pixel, and two green pixels in the array. And from that, we can work out the color that's present, the actual color that's present in all four of those pixels. Now, an interesting question actually to ask is, why do we have one red, one blue, and two green? And that's actually quite simple. Is because if you go back to the first slide I showed, which shows the embedded electromagnetic spectrum, you'll see that at one end is the red, and one end is the blue, and the middle is the green, and the middle is the green element of the human visible spectrum. So we're actually more susceptible to green elements of the wavelength. So we have two green pixels for that, one red and one blue to cover either end. So once we've got this into our FPGA, we're going to be working with these color spaces, and there's a range of color spaces that we can use. Now, what we're going to get from the sensor today in the applications that I show you and that I demonstrate, we're going to get a raw image from the sensor. So we're going to get a raw A or a raw, just as you can see at the bottom, a raw A, a raw 10, or a raw 12-bit image from the sensor, and that's going to contain just the particular elements of light, be it red, green, or blue. Once we've converted it and we've gone through our debayer, our demosaic, as we call it in the Xilinx world, we're going to end up with typically a RGB pixel, which will be represented by a number of bits. And most commonly, we represent it by 8 bits for each channel. So 8 bits red, 8 bits blue, and 8 bits green. And we have a 24-bit pixel. Oftentimes, though, we might want to use the luminance and the YUV color scheme, which uses luminance and two chrominance channels. And essentially, then you have a luminosity value, which is Y, and then two elements, which are the Y, the U and the V. Now, interestingly, if you can use the YUV, essentially the Y channel is a black and white image, and the U and the V eventually give it the color. And we can use this using IP and the Xilinx IP to convert between the RGB and the YUV color space. Typically, if we do that, we're going to end up with a what they call a YUV 444. And again, that's going to be a 24-bit pixel. Now, when we move these into memory, when we move these into DDR memory or anything like that, 24 bits is not necessarily always ideal, because we have to use 32 bits to store 24-bit. And it's not the best way. It's not the most efficient use of memory. So what we can do is, it's quite common to actually use YUV 422, and in that instance, you get a 16-bit pixel if you're working in the 8-bit domain. Because what happens is you provide new luminance values for each pixel, so new Y values for each pixel. But actually, the Y and the U and the V elements you share between two pixels. So on one pixel you send the luminance and the U, and the other one you send the luminance and the V. And from that you can both pixels use the U and the V that's shared between both of them. So you can have a nice, more efficient memory architecture. for your 16 bits. Now, all of this actually we're going to be doing today on this example. We're using the Ultra96, the V2 version of it, and with this we've got the processing system. So half of this device contains high performance processing system, and this is the master. Essentially, just like any other traditional processing system, the processing system is the master. So it boots first. It contains everything we need to run just as a processor if we wanted to. So it's got the ARM A5s in it, the R3s. It's got memory controllers, and because it's dedicated hard silicon, it's actually, you know, there is configurability. In fact, there's a lot of configurability, but it's not as configurable as the programmable logic is. So there's limited configurability there. And then obviously we've got the programmable logic. And this is really ideal for doing large parallel operations and accelerating applications. So within here, we've got dedicated resources. So not only the configurable logic blocks, but we've got DSP48, we've got block RAMs, we've got high-speed serial interfaces. We've got really, really flexible I/O. We've got system monitors in the XADC, which is really useful if you want to begin to think about the prognostics and the diagnostics for the safety cases downstream. And we've also got a number of interconnects between the processor system and the programmable logic. And between that programmable logic as well, we can get clocks and resets and interrupts and everything we would expect to be able to make the best use of that tightly coupled processing system and programmable logic. Now, this gives us some real benefits when we come to creating our system using one of these devices. What it means is that on our processor system, we can put the high performance applications running on the application processing unit. We can leverage the real-time processor. We can leverage a real-time processing unit for the hard real-time stuff that we need to implement. You know, so interfaces with automotive driving systems, braking systems, that can all come from the real-time unit. We can put really high level, because we've got the APU in there, the application processor unit, we can leverage high level algorithms running on those. So we can run, as you'll see today, we're going to be running embedded Linux on that, and we can really pull in really industry standard frameworks and such like. We've got really the R5 and the programmable logic is really designed for creating that safe and secure solution. So like I was saying, it's designed for interfacing with the braking systems, with acceleration, with driving systems. So it's designed to comply with ISO 26262, IEC 61508. We've got a range of interfacing options in there, because obviously interfacing is really key to our applications. It's really key to whether we win or lose our design. And we've got, as you'll see in the third lab, we've got the ability to accelerate functions using OpenCL. Now, the programmable logic, that brings us a whole new element to this development. Obviously, we get any-to-any interfacing. So we can, if we're pin-bound or we're interface limited, we've got pretty custom interfaces. We can implement that in the programmable logic. The MIPI interfaces that we're going to use the MIPI define, that's all built in to the I/O structures of these Xilinx FPGAs that we're going to be using. So that saves us having to have things on the board and do elements there. We can have a true image processing pipeline. So we can move away from having stages in DDR as we move between different processing stages. We can have a really true image processing pipeline that moves from one to the next and that's going to allow us to get through the system quite quickly and hopefully. Now, our system's going to use MIPI, and our solution uses MIPI. So I really should introduce what it is, and it stands for the Mobile Industry Processing Interface. It was really kind of popular it's really popular in mobile phone industries and such like that, and it's a point-to-point protocol that allows us to share either image or data or display data, depending upon whether you're using the MIPI CSI or the BSI standard. And at the lowest layer, it uses the MIPI define, and it defines clocking, lanes, and signalings, as you can see in the image on the slide there. So it provides us a number of data lanes and a synchronous clock lane, and all the transfer is double data rate. And we have an I2C configuration channel for configuring the imager itself and reporting back on status. Over these 4 lanes, we can get up to 10 gigabits per second, which is really quite important. we have this bidirectional I2C control, which is really important for being able to configure the camera in the mode that we want to use. Now, the only downside with MIPI is that if you want to use it on a board type application, if you want to use it in your application, due to the data rates and the technologies, it's limited to roughly 30 centimeters due to signal integrity type issues. Now, if you think about your car, that's not so good, because what we want in the car is we want to have one central processing element, because cost and weight are key, and we want to have several MIPI cameras scattered around the car, as we were saying. So the solution to this is to have a single processing node, as we were saying, which uses the Zynq MPSoC, and then actually to get around this 30 centimeter limitation, we can use high-speed serialization that interfaces directly to the MIPI sensor. So it takes the MIPI signals from the sensor. It has the I2C signals as well. It serializes it over a coax link, and then the receiver converts that high-speed serial back into a MIPI format and has again the I2C link. So to the Zynq MPSoC that's working, it looks exactly like it's talking to just a MIPI device, but in reality, it's talking to one of these high-speed serializers that's moving this data up and running. Now, because we've got this and it uses a coax type technology, it's really possible to have really long runs of cable around your car and around your vehicle. So we can do this, we can distribute this around the car. And the other thing that's great about MIPI in the automotive world is we're not going to use it so much today because obviously we're in the prototyping side, but when you're talking to your imaging suppliers, your sensor suppliers and your sensor systems, you might want to put safety data on the sense of the sensor performance in the MIPI stream. And you can do that and send it down using a virtual channel. So as at the receiving end, the Zynq can literally just strip off the safety information, take the safety information, do the safety processing to check that the image is working okay, and it can pass on the final image. In our Xilinx FPGAs, it's really easy, really simple to configure, as you'll see in a moment when we go take a look at Vivado. What we have it's just this simple dialog box to configure the MIPI interface exactly as we want. We have the DPHYs inbuilt on UltraScale Plus devices, so that's already there in the I/O. If you've got the 7 series or UltraScale devices, you can implement MIPI solutions one of two ways, depending upon the line rate that you want to work with MIPI. So up to about 800 megabits per second line rate, you can get away using an external resistor network that gives you a MIPI compliant interface. Above 800 megabits per second on the line rate, then you need to actually implement it in an external PHY. But there are several external PHYs available to do that. So somebody just asked a really, really great question about the significant latency, which is using the GMSL between the camera and the MPSoC. And on the applications that I've seen that have used this, I've never actually seen latency be an issue. These coax cables, they're going at quite a fast data rate. And typically, in the applications I've kind of worked on in the automotive domain, you want to have really from capturing the image to making a decision and working on that image, you really want to have about 1 frame's worth of latency in there. So it doesn't really cause a huge issue in my experience. And I'm aware, I've mentioned GMSL, but there are some really even better technologies coming out later on this year that will do that. So coming back to our MIPI application, so within the Xilinx FPGAs, obviously being able to work with MIPI is really important. We've got the I/O structures, we've got the DPHYs there, and we can do that with the CSI. So we get an IP core solutions, as you can see, for the CSI2 and the DSI solutions. And a lot of people are sat there going, this is great, but MIPI cores are really quite expensive. But actually, from the recent release of Xilinx 2020.1, so Vivado 2020.1, Vitus 2020.1, the IP cores, the MIPI IP cores are actually free and don't need any licensing to go for it. The examples I've created today, we're all in 2019.2. And because we're in 2019.2, you just need to ask for if you want to recreate any of the examples that I've created that I've put on my GitHub, you just need to go to the Xilinx licensing manager and just ask for a free evaluation license. So what we're going to look at today, as we run through this application, is we're going to look at creating this initial image processing path that goes from, excuse me, been talking for a little while now, that goes from the input processing through the processing algorithms, moves the information into the processing system, and then outputs it onto a display. So the very bottom row of these devices is what we're going to be looking at in our first implementation. So these elements here. In our second lab, we're going to be looking at particularly what's in the processor in the implemented algorithms running the pink. And then in the third element, we're going to be looking at how we can create and do this, where we move applications off from the processor into the programmable logic. So it's going to give us a really good explanation of what we're going to be doing. So first off, we're going to start with lab 1, and I'm going to explain to you how my design for the embedded vision system that we're going to use as the base. Katie's hopefully going to keep me to time when it's time to come and talk about talk to Kevin about about some of the questions in our fireside chat. But first, we're going to take a look at the embedded vision system, creating this baseline embedded vision system. And there are 3 elements involved in doing this. The first one is within Vivado, we're going to create a hardware design. And in that hardware design, I'm not going to use any custom RTL or any high-level synthesis or anything like that. I'm literally going to create an image processing pipeline and explain the image processing pipeline to you using Xilinx IP. That's all there in the catalog. And actually now, because of 2020.1, all the IP that I've used in there will be free. Once we're happy with our Vivado platform, we're going to build our Vivado platform. We're going to build the Vivado platform. We're going to export a XSA, the description of the hardware design and the bit file, and we're going to export that into Vitis. And within Vitis, we're going to create an embedded flow platform. So we're going to create an embedded software platform, a typical software platform that we would use for doing our embedded software development. So no acceleration just yet. We're just going to write a nice, simple, bare metal application that just gets used for this application. And then finally, within Vitis, once we've created the platform, we can write our application for it, and then we can download it and run it onto our hardware target, and hopefully we can get that working there. So now what I'm going to do is I'm going to just close this screen for a second, and I'm going to open up Q&A again, actually, so as I can see what's been said on the Q&A. And we're going to open up, and hopefully you can see a Vivado design. And over the next 20 minutes or so, I'm going to work you through this design and the design element within Vitis that we used to create this design. So first off, like I said, we're in Vivado 2019.2 because that was the latest version when these reference designs were created. Although if you wanted to upgrade them to 2020.1, I don't see that it would be a huge issue. What we want to do is we want to get rid of that and maximize my screen. And what you can see here is I've used a block design to create the application, a nice simple block design approach. And what we've got is we move across the design from the input to the output. Now, to get us started with this, obviously we've got the Zinc UltraScale Plus processing system in the middle, and this is created from a project that is already aware of the Ultra96 version 2. So it's got the board definition files included in the Xilinx board directory, in the Xilinx Vivado board directory, so it's board aware. And within that will configure if I double click on the processor to customize it, that will configure the processing system exactly for the Ultra96 board. So it will set all the clocking up, it will set all the DDR interfaces up, everything that we need to get going and start developing will be created and enabled with it. It takes a few seconds normally it's quite quick, but actually when I find when I'm sharing my screen and broadcasting information, it takes through. So hopefully that's going to come through in a moment. And here it is. So we can see we've got the MPSoC element sat there, and I'm going to make I made a few modifications to this because we want to be able to obviously control and configure. As I said, I'm going to use IP cores to pull this IP, to pull all the IP, the information through the image processing tree. Now, what's really important with that is that this is all going to be software configurable in Vitis as we move forwards. And that means we need the ability for the processing system to be able to access and read and write those registers. So we need to look at our processor interface and make sure that we've got at least one master interface connected and enabled such that we can connect to the AXI control inputs in the processor and get that in the IP blocks that we're using and get that going. And hopefully that will get us going and get us moving. We also actually, one of the key things that we want to do is I want to move the data across into the processing system DDR using VDMA. So to do this, I need to actually use a slave AXI port on the Zinc, because the programmable logic is going to be the master. It's going to be the initiator. So it's going to be the one that writes into or reads out of the processor DDR system. So I'm going to enable I enabled the high performance port 0 for the application, and that hopefully will allow us to see the system going on and then be able to transfer this data to and from. I'm also going to, under the more general element of it, we're also going to enable the resets, the interrupts from the programmable logic to the processing system. So we're going to enable the IRQ0 in there. So I've enabled and set it up for the processing system. And I've set the clocking configuration up as well to provide me just a simple clock. So I just want a simple 100 meg clock from the processing system. I'm going to use many other different clocks in this application as we move through the free tutorials, but actually just one coming out of the programmable logic for the time being is sufficient. Within this programmable logic system, then we're going to move through, and I'm going to zoom in a little bit now onto the system that we have. So we're going to start out at the beginning. We've got our MIPI coming in. So we've got a MIPI CSI2 RX core. This is the MIPI2 interface. And if we double click on that, we can reconfigure that to our heart's content to make sure that it works and it functions as necessary. We will get through that, and we will once this opens up, we can. This is really key because within here we can work out how to connect not only how to configure the device, so we can configure the pixel format that's coming down. So it's going to come down in a 10-bit raw format from this sensor. We can configure the MIPI line rate. We can set up all the CSI2 options that we have. If we have multiple MIPI interfaces, then we need to consider the shared logic, and that's whether the MCMs and the PLLs are included within this design. Or they're included within another IP module, and whether it's shared. But because we only have one, we need to include it within the core. And then crucially, this is where we set up our pin interfacing. So we don't need to write a XDC file to get this working, get this application working for the MIPI pins. We just need to tell it the pins that the clock lane and the data lanes are on in the MIPI subsystem, which is what we've done here. So you can see we've got a dual lane. This is a dual lane MIPI sensor. So the dual lane MIPI sensor and the clock there. it needs to work. So to work, this needs a 200 megahertz. This needs a 200 megahertz reference clock, which is provided by this first clocking wizard here. And this first clocking wizard here provides all the clocks for the image processing chain. So I want to output a 720p image at the end of the day. I want to output this 720p image, and I'm going to use a display port to output that 720p image. So I'm going to clock this. I'm going to generate two clocks, one at 200 megs and one at 150 megs. So that's double the output pixel clock for a 720p output, which is a shade. It's a weird number, but it's a shade under 75 megahertz. So then we step through our image processing chain, and our image processing chain is actually, in this application, is fairly straightforward. What we've got is a demosaic. So this is if you remember back, I was talking about debayering. So this is the element that does the sensor debayering. And what you can see is it brings in the AXI stream video. So the AXI stream is how we transfer video at high data rates within our image processing system. It's a unidirectional stream. There is literally just the data, the T-ready, the T-valid signal, and then there are two sideband signals which are used to indicate the position in the image, so that we can reconstitute what would be an infinite stream of pixels into what would be a two-dimensional array at the end of the day. So these are the T-user sideband signal, and a pulse on that indicates that it's the start of a frame, and the T-last signal. And a pulse on the T-last signal indicates that it's a last line, it's a last pixel on a line. So that image interface is streamed in there. We've also got this interface here as well, which is the clock, which is the AXI configuration interface. So this is the interface that we're going to tell it in our software what the configuration is, what the debayer pattern mask is, because this can work with several applications, and what the width and the height of the image are, so as it knows how to go about doing it, and actually when to start running. We're going to do all that. We have an AXI subset converter, because the pixel is going to be the camera is going to actually put out an 8-bit, going to put out a 10-bit pixel. But actually, I only want to work with 8 bits. It's going to make it a lot simpler as we go through the day. So I just have a simple subset converter just to slice off the bottom 2 bits of the output pixel, and then the rest. And then we have a gamma correction, gamma lookup table correction unit. So this allows us to correct for gamma in the image. So it allows us to change very slightly the intensity of the image depending upon the incident light. The very eagle-eyed as well will have noticed that I have a number of internal logic analyzers inserted within the design, and these internal logic analyzers are used to verify the various stages that we're moving through in the processing application. So they're there to check that we can get an image coming out of the MIPI sensor, that we can get an image, that we get data flowing through that first demosaic, and we're moving through into this. We also have the VDMA element, and this VDMA element is going to be what takes the image stream and pushes the image stream into the programmable logic, into the processing system DDR memory. So this VDMA, it writes it into the processing system DDR memory, and it's going to pull it out of the DDR memory as well for our output. We also have an AXI subset converter on the output, just to change the position. So we want an RGB pixel, red, green, blue, but actually the pixel stream as it's flowing through is red, blue, green. So we need to flip over 2 pixels before we output it, just to make sure that we get the colors correctly in the correct positions. And you'd see that very easily if you didn't, because if you put a blue car, for instance, or a blue image in front of the camera and those were flipped around, then it would appear green as opposed to appearing blue like it should be. So this is all quite straightforward. We've enabled in the Zinc processing system, I've also enabled the display port to be fed live from the VDMA. So there's a couple of good questions here. So someone was asking if we have why have I used the VDMA and not the frame right? And actually, in the later project, in project 3, when we start working with pedal Linux and with the acceleration. I do actually switch. We will be switching out the VDMA to have the frame right IP in there. But for the bare metal and for the pink application that we're going to be looking at next, actually the VDMA it makes our life slightly easier. So we've got the VDMA. It's literally, when it comes to it, it's literally just swapping one block out with the other one. Someone was asking actually if the VDMA can scale the video to different resolutions, and the VDMA can't. You've got a couple of options to do that. You could do it in software, which would be quite inefficient really, or there's an IP block called the video processing subsystem, and that has the ability to do that scaling for you. So if you need to do some scaling, then that can do that, and you could just implement that in line before the VDMA, for instance. So perhaps just after the gamma LUT would be where you would do that. Is the VDMA capable of rotating? So somebody's just asked if the VDMA is capable of rotating the image by 90 degrees prior to pushing the memory or popping off the memory, and the answer is no. So again, the options for doing that would be to twiddle that in software yourself, or to write a simple HLS block. Actually would take about 5 minutes to write that, just to rotate the image around. It wouldn't be very tricky at all. So once we've got the VDMA, we've got the display port enabled on here. We've then got a traditional output path, and the reason I've shown this traditional output path as opposed to just using the kind of the hidden VDMA, the hidden display port configurations that we could use on the processor system side, is because your follow-on applications might not want to use that display port. They might want to use HDMI or a different type of interfacing. So this just shows you how you can go away and do that. So once the image that's pulled out of the VDMA is then pushed through this AXI stream to video out. So this takes the AXI stream that we're getting it and converts it much back into that traditional framework that you would expect for video processing of horizontal sync, vertical sync, active pixels, and the parallel pixels themselves. Once that's output, actually, we then just connect it back into the DisplayPort input. So Tim's just asked a good question about how we could store the video stream. So we could put it onto a USB mass storage or an SD card. In this example, this is a bare metal example that we're showing here. And the reason I'm showing a bare metal example is this is the really simplest way to get everything up and running and to prove that your Ultra96, your MIPI board, and your camera are all going to work together and you can get an image flowing through it. Once you've got an image flowing through it, you might want to do some image storing. And I'm going to show you in the next instance when we look at the Pink Lab in session 2, I'm going to show you how we can record video directly from the Pink board and create AVIs and videos and pull that if we want to. We can save that to the SD card, we could save it to the USB mass storage, or we could even, because Pink's networkable, we could even write it to a server over Ethernet. For the avoidance of doubt, in my example, I'm going to save it to the SD card because it's the simplest way forward. So this gives us a really straightforward, really simple, really nice, plain IP design, and it just flows through from one element to the other. What we need to do then, obviously, once we've got this, is we build the design, we take the design and build it, and we can export it into Vitus. And once we've exported it into Vitus, we need to do two elements. I'll just move that back into a display type. The first thing we need to do is create the platform. Now in Vitus, the platform is actually going to contain for a simple embedded application. It's just going to give us the board support package, so it's going to contain all the drivers, all the applications, everything we need for the everything we need for doing the APIs and getting us up and moving. So we'll be using that. Once we've created that, and literally we just give it the XSA and it will create the board support package for us dead easily, we can then create our application. And in this application, I've gone through and I've created a very simple project. Hopefully it's going to open. And you can see here, it's just pulled, we've just pulled in all the peripherals that we've got in there, the controllers for all the peripherals that we have in there. And we have all the definitions for the software that we need to use, all the gamma calculations, and then a really simple application that just runs through, talks to the camera, sets up the video timing application, sets up the frame buffers in the processor memory. And like I say, you can go to my GitHub account if you want to take a look at this and download this all to your heart's content. Takes a look, pulls all this through, so it sets up the DMA, sets up the demosaic, sets up the gamma LUT with the calculated gamma values that we have, and then starts the camera up and going. And then once the camera's up and going, we run in an infinite loop. There's a couple of functions in there to detect the camera, so we can have one that detects the camera and one that downloads these settings to the camera as well. And we have a very simple gamma LUT calculation. When you put all this together and build the application, we can then create a simple debug configuration, which is just going to open up. So we create a simple debug configuration targeting our board, which is connected to it. We ask it to reset the system. We ask it to program the FPGA and run the power up. And when I debug this, if I just quickly turn off my, okay. If I just quickly turn off my background, so as you can see my back screen, what I can show you is that while it's downloading, what I can show you, I can take my webcam and I can show you down here. We have the Ultra96, the MIPI camera. The MIPI camera is held in this little gadget. I have 3 cars: a blue car, a grey car, and a yellow car. And we have a screen here as well, which is displaying on the DisplayPort output. And hopefully, if I click run on the software, along with the run on the software, we will see the image begin to spring to. We'll see the image begin to spring to life. So you can see the cars there as we move them about. You can see me moving the automobiles about. And interestingly enough, although my light behind here has just turned itself out, you can see the car that is blue, the car that is yellow, and then we can see all the systems that we have for the application. So what we see there is that the application's actually up and running, and we've retired the risk then of getting the image processing system and all the 4 or 5 systems that we've got up and running, and we can now start to focus. Now we know we can get an image through it, we can get the basics through it, we can configure it. We can now start moving on to that next element, which is using the pink and starting to develop our own algorithms. So that's what we're going to look at in the next session. But first, we have there's a question that I want to answer just in the session coming up. But first, we have a quick question that someone said was, what would you do to ensure the camera output is basically correct? For example, white color order, or the utilizes the whole bit depth. Would you debug it in the PL or the PS? So I would actually begin to debug it in the PL. So I would use some of those internal logic analyzers that I've put in there to make sure that I'm sending data through, to make sure that the picture looks pretty good. It looks a little dark on my screen because it's a little dark in that corner of my office. But I would actually do a 2-phase approach. Like I said, I'd debug some of it in the programmable logic to see that I was getting the data through and passing the data through. And then actually, once you can see that, I would do something such as hold some color charts up, some color bars up to it, to make sure that the color bars were as we would be expecting, and the screen and the colors are all in the right order. And then you could do some more tests to start checking all the color depth and the pixel depth. So I've wrapped up now. Katie's back, which is good. So I'm only 5 minutes behind schedule.
Hey, we're doing great. Thank you so much, Adam. So we're going to invite Kevin Kirk to come on and join Adam for this first fireside chat. So Adam and Kevin are going to be talking about making the transition between development and manufacturing. And also just a quick reminder, if you do have questions, just type them in the Q&A section. Adam's been doing a great job of keeping up with those and answering those throughout the session. So again, during the chat, they might kind of come in and answer, and we'll also have a 15-minute section at the very end of this where you'll get to ask your questions as well for anything that you missed or need more elaboration on. So thanks, guys. I'll let you get started on this chat.
Thanks, Katie. Can everybody hear me okay?
Yeah, we can hear you.
Oh,
Great,
good.
Kevin.
Hi,
So
Adam. How you doing?
I'm doing magnificent. How are you?
I'm doing great. Thank you. Thanks for having me on.
No problem at all. So one of the first questions I wanted to talk to you about actually is in this session is what I've done really here is I'm kind of showing the hardware for a prototype. And obviously at the end of it, we're going to have a really nice prototype and it's going to do a lot of risk reduction. But what options do I have, say, if I want to take this prototype and then take it forwards into production? What are my options available, and to make it as simple and low risk as possible?
Yeah, no, that's a really great question. Before I get to that question, Katie asked us to stop the screen share so that way our video expands out and people can enjoy our little fireside chat here.
I will do that. I've stopped my video.
All right, looks great. Thank you. So yeah, the question you're asking, Adam, once you're done proving out your concept works, how do you go from going from a concept, at this really prototype stage, into something that's a reality, that you can implement inside the system? So I think you talked a little bit about Ultra96. I have one here. So I'll talk a little bit about that one. That is not only our low-cost development platform for Zinc UltraScale plus MPSoC, but it's also a single board computer. So it's kind of limited in terms of I/O because it's such a small form factor single board computer, but it's at a really great starting point for most people to start experimenting with that platform. Comes in a little box like this. Very nice graphics here on the box. Available from Avnet and also from our newer outlets. But if you're looking for something with a little bit more heavy-duty I/O resources, let's say you want to integrate more sensors on your board, we have these system on modules, and this one's an earlier prototype version of the UltraZ EG SOM. But this is a SOM that Avnet has designed in conjunction with working with our supplier partners. Obviously Xilinx is kind of like the center of this device right here, and the heat sink's falling off there. Let me pop it off. You can see it right there. But we also work with other supplier partners to design the components onto those SOMs so that they meet the requirements that people need for more advanced applications. So hopefully that helps answer the question, that the system on module approach is a very popular one for folks that maybe don't have the time or the resources internally to do a chip down design, and they're looking to launch their product using something that's already pre-made. So it's the sort of make versus buy argument. That can help really get people in the market faster when they leverage an Avnet SOM.
Okay, so somebody actually just asked a question as you were talking, which I think is really good. So you mentioned that it was a low-cost solution. So have you got any kind of indication of what it's likely to cost price-wise?
Yeah, no, that's a really good question as well. So let me go ahead and I'll click on that answer live button here. I'll answer that live. So the Ultra96 single board computer, that's our lowest cost application of Zinc UltraScale MPSoC. That one's available for $249 US. So that would be the lowest entry point. And that's also a production solution. So we temperature test that across an industrial temperature range. There's an industrial version of that. The next one would be our UltraZ SOM. So that one is under $500 US, and the price obviously goes down as your volume increases. So if you're looking to deploy that, in less than 1,000 piece quantity, you can work with your local Avnet FAEs to place an order and get that better pricing than what you see on the web. In fact, let me while I'm at it, let me just paste a few links into the chat here, so that way people can take a look at some of the things that we're mentioning here. So go ahead and I'll paste the link for the Ultra96 into the chat. I also have a link to the UltraZ EV platform. So it's a little bit heavier duty platform. This is more of our premium solution. This one has a Zinc UltraScale MPSoC EV version of devices on there. And the thing that's special about the EV is it has a dedicated video encoder on there. So for the application where you were talking about encoding video down to a local device, that could really help out, because then you don't need to worry about doing that video encoding inside of software. There's a dedicated IP block that's built into that chip that can do it. I believe it's doing it faster than any of the other commercial chips that are out there. So it's a very, very high, it is a higher end solution. There's obviously additional cost to that platform over what you see with Ultra96, but you're getting a lot of capability with that platform as well.
So one of the other things you mentioned, so we had this SOM, and which is really great because it minimizes the risk, you know, of designing the board, getting all the DDR timing correct and putting it down and everything. But I still need to kind of create a mission card, an application interface card to sort of interface with my sensors or with my systems. Do I have to do that myself, or can you guys help us with that as well?
Yeah. So we provide a lot of flexible options depending on what your capability is. So I had mentioned, here's our UltraZ EV. This little board here in the middle is the actual SOM right here. So this little rectangle piece right here. Yep. So that's a what we would call a production module. We test that to some pretty stringent standards over industrial temperature range. We have industrial temperature range versions of that. This board around it is what we would call a carrier card, or maybe you'll see it as listed as a baseboard in some documentation for some folks. But we can provide, through your Avnet FAE, we can provide those design files to you as a starting point. So you could customize that yourself. You're capable of doing hardware design yourself. We also have Avnet design services. So if it's not something you're comfortable with doing yourself, that is something that we offer as a professional service here at Avnet, depending on what type of design it is that you're looking for. We work with all sorts of supplier partners that are on our line card, just to name a few. Obviously, Xilinx is the centerpiece of the SOM, but we also work really closely with Micron and their engineering team to make sure that we have the latest and greatest memory devices on there that have long-term support. We work with other suppliers such as, Maxim is another one. So you mentioned the GMSL parts on there for doing automotive. We work really closely with Maxim. In fact, we actually have a board, an expansion board called an FMC Multicam 4. So let me just post a link to that really quick, so that way folks can take a look at that if they're looking at automotive applications. It actually comes available as a kit. We have a bundle that has the AR0231 AT sensors that you had mentioned earlier. That's a really great sensor for automotive applications, and it's also a great way to get started with those Maxim GMSL devices.
No, I think those good, those mission cards, those carrier cards, those interfaces. I think they're a really good application and help us get going quite quickly. I mean, I guess when it comes to it, you might want to sort of be creating your own custom hardware and developing that. And then you've got all the worries about sort of making sure that your devices meet the compliance with the various industry standards, the 26262. So do you stock the XA range of devices and provide support for that via your FAEs?
Yeah, no, that's a really good question. So Avnet is, we're a distributor for all Xilinx parts. And so we do have the ability to have to sell the Xilinx automotive parts. That is definitely an option. There's other pieces that Xilinx also has available that are interesting to folks, such as the isolation flow. In fact, I did a little bit of research on that. I found a few links that might be interesting to folks to take a look at. I don't know if these are mentioned later on in the presentation, but let me just go ahead and paste this.
I've not mentioned too much about the isolation flow. I don't know what your links are, but I know I've certainly written some blogs on it on the MicroZ Chronicles about it, and when I teach about high reliability design, it's always one of the key things I talk about is that isolation flow and the support in the R5s as well for the ISO 26262 and so on.
The XF 1335, that one's a really great place to start, where it talks about the isolation design flow. Just some things to think of during your design are, modular redundancy between the logic blocks. In case something goes in one safety critical logic block, you have another one that can serve as a backup for that. Another thing would be to set a watchdog alarm in case of, some portion of the circuitry is not responding within a, predetermined amount of time. Yep, that you'd be aware of that, and that you could reset the circuitry if needed. And then another topic that's covered is segregation by safety level. So depending on what your safety level is for your automotive application, you can actually segregate different pieces of that logic to protect other pieces. And then another key part too is isolation of the test logic for safe removal. So you could instrument up your logic with a bunch of test benches to test it out ahead of time. But one thing that I found over the years in designing that is you want to make sure to isolate that test logic. I'm sure we've all run into some really strange bugs during our development. I've run into interesting bugs. Some of the old timers that I work, they would call them Heisenberg bugs. So basically the bugs that exist until you go to try to look for them, and then all of a sudden they disappear. So you got to be really careful when it comes to doing debug that you're not introducing additional problems into your system.
It's like when you insert it's like when you insert an ILA to find a problem, and suddenly the problem disappears because the insertion of the ILA fixed it.
Yeah.
Just make you wonder how many designs are floating out there that have got ILAs in there. Just 'cause if you take it out, it breaks. I mean, there's some really great. There's a really great flow actually to allow you to do that without actually changing your underlying of the design. So I just want to come back actually to a question somebody's just posted in the question and answer channel, which I think is really quite interesting. It's got a good one. So someone was asking, so if the Ultra 96 is good, you're saying it's a SOM in its own right, really. So if it is and it satisfies the product requirements, is there any restrictions by Avnet on its use? Can anybody use it for any application, or is there anything that would limit you being able to use it on your project?
Everybody has to evaluate their own risks on their platform. Our SOMs are all tested to industrial temperature ranges. If somebody needs that tested to an automotive safety standard, that's something that we can certainly help out with. And professional engineering service level, we do work with test labs. That's something that we can help out with if somebody's needing help with their automotive design. But in terms of end application, you have to make sure that the devices that you're choosing and everything, those match the needs and the safety risks that you're taking on for your end application. But Avnet's here to help with that. If you do need help, you can contact your local Avnet FAE, and we can provide a customized level of service around that.
Oh, that's really good. That's really good to know. I mean, one guy else. Another question actually came in, which I think is an interesting one we should touch on now, before we move too far down it. And somebody's asking, you've mentioned low cost several times and about the Ultra 96, but this is an interesting question about what's not possible with the Webpack. So what, that most people, the Webpack develops, it supports the Ultra 96. Some of the other devices are, some of the more high-end devices are limited. But what's not possible for the devices that you've talked about today with the Webpack? Is it limited in terms of just devices, or is there limitations in terms of HLS and IP or OpenCL capabilities that you're aware of?
Yeah, so for some of the higher end devices, we're talking about, very, very large logic devices. Those ones are not supported by the Webpack, but for all the devices that we mentioned on our webinar today, including the Ultra 96 board, the Webpack will support all the pieces that you need for development, including the MIPI IP blocks. So I was in discussion with Xilinx about this, Adam. I don't know if you're aware, but the 2020.1 tools, those ones actually include a free Logic Core MIPI IP block. So that's really great news too, that nobody really needs to pay for the MIPI block anymore.
So the entire example we've created today and have made available is now free. It's brilliant. It's a really enabling step, was that making that MIPI tools free.
Yeah, so it's a really great time to be designing new platforms with Xilinx. With that Webpack, you get access to so much functionality right out of the box. And as long as you're targeting these more entry-level devices, it's going to be completely free for development.
That's good. I think it's been a really interesting sort of chat and introduction as we've had, as we talk about this, what options we've got as we want to think about taking it further forward and taking it into production. Let's just wrap up with just one last question. I think it's a little bit of a recap, but somebody's just asked what solutions are there for multiple cameras. So obviously we're showing in regions of time, because if you have one, how to do one, because you can scale it. But say I wanted 4 or 5 cameras in my system. What solutions do you have for that?
Yeah, that's a really great question, and it's a actually really great application for an FPGA because you're really only limited by the number of logic resources inside the device to add additional cameras. So, I had mentioned that we have that the multi-camera FMC. That multi-camera FMC, it's my understanding. I haven't done this myself, but there are actually enough resources on that FMC connector to add up to 12 camera modules to your platform. So if you have an automotive application where you need to have, side view cameras, rear view cameras, forward facing cameras, driver facing cameras, all tied into one platform. If you have a large enough logic device, you could implement that all inside of a single Xilinx device. So that's the unique portion of using a Xilinx device, is that it has the ultimate flexibility in terms of scalability, that you can scale it out to a number of different camera devices, where if you chose like an ASSP, you're kind of limited by however many cameras that ASSP was designed to support. So I think there were a few other questions that came across here in terms of certification and documentation and availability. So before I head out, I just want to paste one link in here. So this one's regarding the SOM lifecycle. So vehicles have to be manufactured over quite a bit period of time. So if you're looking to support that long term, Avnet's here to support you with that. I posted a link in there to our SOM life cycle. Every SOM that we build as a product, we intend to build that for at least 10 years. So as long as there's interest in that product and people are actively buying that product, we will work with our supplier partners to continue to build that product. It's my understanding, we do have one product that we still build. I believe that product is over 14 years old because folks have purchased that SOM because it was actually a Vertex 4 SOM that we had designed quite a while back, and so we're still selling that one today, even 14 years later. So that's something that you won't get from a lot of the other providers out there, but Avnet's here to stand behind our products and help people be successful with building their own end products by using our Avnet branded products inside of them.
So that's really good, and I think that commitment to the long term is really quite admirable and quite keen. Obviously, it's a really important thing for several markets, not just the automotive one, but it is really good. So I think we're taking up all the time that we have for this chat. It's about 1:15. So I think I'm going to let you go, and I'll speak to you again. I think you're going to come back to me and talk with me about what we've just done with the pink environment in about an hour or so. But thank you very much for your questions, your comments, and everything there. And then we'll move on, and I will speak to you in a little while.
All right, sounds great, Adam. I'm really enjoying your presentation. It's really very, very interesting. I love watching.
Well, that's good. Hopefully it keeps most people awake while we're going through it. It's midday, early evening here, but it's still very early by you. So we'll get going. Right, I'm going to share my screen again. Okay, so now we've completed our design in the first element, and what we've done in that first element is we've created a bare metal design that takes us through the camera input to the camera output, and that really allows us to demonstrate that what we've got working is a camera that we can correctly drive the camera with the hardware that we've got, the configuration that we've selected, and of course that we can display the output on a display port. Now that's a really good step in our way of prototyping, but actually what we need to do next is begin to focus upon how we might actually implement algorithms on there. And one of the key things we want to do is determine what the algorithms are and using those algorithms with the real world sensor. So we don't really want to be running them on a desktop machine using frameworks and beautiful and perfect images on a machine. What we really want to do, if possible, is to be using the real world hardware, the real world sensors, but perhaps, just perhaps, not getting the absolute peak performance that we could, because we're still focusing on the algorithm development, the processing development. We know that in the next step, when we take a look at Vitus, that we can do the algorithm acceleration. Our key thing in this point of the process is to be able to determine the
correctness of the algorithm and identify the algorithms that we want to run. And we want to be able to do that quickly. We want to be able to do that quickly, fast and easy. And how we're going to do that in this example is we're going to use Pink. So what is Pink? So Pink is an open source project that comes from Xilinx, and it allows us to combine Python, so that really high productive Python, with the performance and the acceleration that we get from the programmable logic. Most importantly, we don't really need to learn any new design skills, or the people developing these algorithms don't need to learn any design skills. For that, we can take the design that we've created previously in the programmable logic, and we can pull this into what's called as a Pink overlay, where we just provide a little bit more of, we just to extract a little bit of information from Vivado as to what the contents of that design are, and we can pull that into the Pink framework, and people can begin to work with that. They can begin to leverage that, and they can see the performance and the algorithm performance that comes with it. Okay, we're still running on the processors, not on the programmable logic, but we can really begin to rapidly prototype, as you're about to see. So the reason why we want to do this is why do we want to use Python to do this? And the main reason is that, you know, Python, according to the IEEE survey, you know, it is the language that everybody is using. And not only is it the most common language that everybody's using, but it's also used across the widest application. So it's used across the cloud and the internet, to the desktop world, and even down in the embedded world where we're working. Python is ubiquitous and spans across all that. And that's what we want to use to be able to create our algorithms as we go forward. So let's take a look at what the Pink framework is. So I've said it's open source and it comes from Xilinx. Actually, it started as part of the Xilinx University project, and it's a really useful framework. It's one of the most useful FPGA development frameworks that there actually is today. Now let's take a little bit of a dive into what it is and to the different levels. So let's start at the bottom and then build our way up the stack. So we have starting at the bottom, we have the hardware design. Now this, and the actual chip, now this will be actually running on the A9 or the A53. In our case, it's running on the A53 quad-core processors that are in the Zinc MPSoC processing system. Those processors are sat there and they're running our software and our Pink framework. But within the hardware, to allow us to connect to that Pink processing system, we've got hardware elements running in there, and this is where it comes in. And within Pink, we've got Pink compatible IP blocks, so IP blocks that come with all the Pink drivers that are necessary to work. Pink's also got massive support for a lot of Xilinx drivers off the shelf, so DMA, VDMA, standard GPIO, AXI Lite type stuff. Pink's got it. But Pink also provides what are called complete design solutions for the programmable logic. So Pink overlays, and these overlays accelerate functions. So they do image processing, machine learning, Kalman filtering, a range of applications that you can see at pink.io. Now, we're going to use our Pink overlay. Actually, our Pink overlay is going to be the design that we created in the previous sector, and that's going to give us the ability to read the camera and output data from the display. So all our processing is going to be done on the program and in the processing system. Now, on top of this processing system and programmable logic, we've obviously got a Linux kernel that's running on the A53s within that application processor unit, and this Linux kernel is actually sat there. It's an Ubuntu-based Linux kernel, and that's providing all the information that we might want to use. Standard processors, standard APIs and libraries and such like. So such as you've got the sysGPIO, UIO, DevMem, contiguous memory allocation, and the FPGA manager, and all those connect over the AXI interconnects as well. Now, moving up a little bit into that level, what's running on this Linux kernel is Python, and within Python, this is where we've got where we really begin to see where Pink comes in for the first time, apart from being at that the programmable logic level. What we've got, you'll find that we've got ability from Python to now control the programmable logic, to control GPIOs, to control MMIO, to work with the DMA and the contiguous memory allocation, and work with interrupts. And to do that, we have the processing system half of the overlay, so the control, the configuration of the overlays, and also a number of Pink libraries and APIs that allow us to do this. Now, what this means is that from our Python application, we can write a few commands, and we can start easily and quickly working with the programmable logic. So we're not stuck in software development world where we've got to wait for the software team to develop the software drivers to be able to do it. We can hit the ground running with our programmable logic design and allow our algorithms team to be quickly and easily working with that algorithm. Now, sitting on the top of all this, once we've got the Pink in there, we've got the Pink package in there with the APIs, the libraries, and such like. Sitting on top of this is an IPython Jupyter notebook, and this allows us to develop our applications using the Jupyter notebook system. And that means that we can be connected to the Ethernet. We can Ethernet connect into our Ultra96 over Wi-Fi or the USB Ethernet dongle, and we can develop away just using a web browser connected to the Jupyter web server on the Ultra96. And that's really important because a lot of these data scientists, algorithm developers, they're going to be really familiar with this Python, this Jupyter environment, and that means that they can start hitting the ground. And the fact that that what's running the Jupyter notebook has changed makes no difference to them, apart from they get much better results because they're working with real world hardware, real world cameras, real world sensors. So like I said, and we can actually create a Pink build for any particular board. So the Ultra96 comes with one, the Pink Z1 does, the Z2 does, the ZCU 104 does, the RF SOC, the ZCU 111 does as well. But if we wanted to create a Pink image for our own custom board, say we've taken the step on and we've created a custom board, then what we can do is we can create this from our own Peta Linux build. And everything really begins with a Peta Linux BSP. If we want to create a Pink build, we start with a Peta Linux BSP, and we clone the repositories that that provide Pink, and then using that BSP and the clone Pink repositories running on a Linux machine, we can easily and quickly rebuild a Pink image specifically for the board that we're working with. And as I said, it's going to be running on the A9 or the A53 processors. We're going to have any overlays that we want in there, and then we're going to add in the Ubuntu-based Linux, the IPython kernel, the Jupyter web server, and then finally we're going to create our application, as you're about to see when we get onto the demonstration element of this lab. So overlays, as I've mentioned a few times and I've explained what they are, overlays are designs that are moved into that are loaded into the programmable logic, and they're generally pre-existing designs. In this example, we're going to be using the overlay from Lab 1. We're going to be pulling that into and using that as part of Lab 2. So that design that we created in the programmable logic is what we're going to be using in this second lab. But say we didn't have that design, say we wanted to work with something else, say do some image processing, machine learning, Kalman filtering, maybe even implement a RISC-V, we can go to the Pink.io community and we can leverage from that Pink.io community a real range of open source community frameworks that are available that we can access from GitHub. And actually what I've done is I've taken this second element, and in the support material for all this, we've actually created a Pink overlay that will do all this for the Ultra96 with all the image processing and everything on it. So it's everything that we need to go and get started and hit the ground running with this. Now, when we want to work with the programmable logic from our Pink environment, it really depends upon what we want to do. There are several things we might want to do, of course. We might want to configure the programmable logic with the bitstream, in which case for that, Pink's going to use the FPGA manager. We might want to use the AXI, we might want to drive some GPIOs from the processing system into the programmable logic, and for that we're going to use the sysGPIO driver. Now, if we've got any asynchronous requests, any interrupts that we want to come back from the programmable logic to the processing system, we're going to use the user space IO driver, and we'll see that being used as we use part of our DMA system that's coming up. Now, if we've got master interfaces on the AXI interface, and that's really where the PS is, the processing system is the initiator of the transaction, we're going to use the dev-mem capabilities, and where the programmable logic is the initiator of the transaction, we're going to use the contiguous memory allocation drivers to do that and to work with that. So we've got this real ability to not only configure the programmable logic, but to be able to drive GPIO from the PS, to be able to work with interrupts, and then to be able to work with the master and the slave AXI networks to communicate, to configure, to control, and to pull back, to transfer data from the PS to the PL or PL to PS, depending upon what's needed. And that's really quite powerful. And as you're about to see, it's really quite simple to do when we use Pink. So before we delve too far into this, I just want to come back and talk a little bit about why we want to use Pink for this application. So the number one thing really is that Pink it opens up this programmable logic to all range of developers. So you don't have to be a programmable logic developer to get the benefits out of that programmable logic using the overlays that are provided via the Pink.io overlays. Obviously, this frees up Python programmers from that sequential software world because they can make experience and benefit from that programmable logic acceleration. They don't, like I say, they don't need to be this design expert. They don't need to know about VHDL, RTL, time enclosure, HLS. They can literally hit the ground running and start working with Python. And of course, it leverages this great community of users and of overlays. So the really important thing is if you create an overlay and it's not specific, it's not confidential, it's not project confidential, client confidential, then please give it back to the community so people can see what's going off there and they can leverage and they can build upon it, because we all get further, if we stand upon each other's shoulders and build upon the shoulders of giants, we all go further together. And it gives us many benefits when we do this. We get a much more responsive solution because we're using the programmable logic, and we can have a truly parallel world. We get a much more deterministic performance because we're not continually going on and off chip between DDR for different stages. We're just running through this programmable logic pipeline. That also means, because we don't have this continual on and off chip, that also means that we're much more power efficient and we get much better dedicated hardware implementation. And obviously, this makes us overall fast. This makes us 10x to 100x improvement in our performance of our applications. And in some instances, you can get much more than just 100x. So let's take a look. As I said, for this application, we're going to use the bit file that was created in part 1 of the lab. We're going to leverage the inbuilt Pink libraries to control the IP. So we're going to create an overlay. We're going to leverage the inbuilt IP libraries that came with that. And that's going to really allow us early de-risking with the main sensor. So not only can we de-risk the main sensor, we can start working with the algorithms. The algorithms guys can start working on it. The algorithm team can start working on it. And they can start working with the real world sensor. And we can use these high level public frameworks, such as OpenCV, and so on, to actually get the image processing working. And once we're happy with that algorithm and that processing, we might necessarily not be happy with the performance, but we can then take that and actually run with it and start looking then at what we can accelerate once we've actually agreed that the algorithmic performance, not the speed of response, but the actual algorithmic performance with the real world sensors is being achieved. And obviously, because we're networked, we can we've got a Jupyter interface, we're networked, so we're seeing the device as a Samba server. We can easily transfer devices to and from the system, so as we can move things to and from the system quite easily. Crucially as well, we can also then get it to record videos if we want in the Pink environment, so as we can see what's going off in there, and we can see what's processing. We can get it to take stills, and of course, in a lot of times when we're doing this prototyping, we're still at the very early stages because we're still working with essentially bits of development boards that we've pulled together that we think we can create a concept from. And we need to get people to buy into this. We need to get stakeholders to buy into this, maybe internal stakeholders such as management systems, or maybe external stakeholders such as investors. If you're a small company or a startup company, and this Jupyter notebook gives you a really nice way to present information and be able to show what's going off on the hardware and make it really easy to create nice little performances for it. Now, if you've never used Pink before, it's quite simple. We connect to it over the Ethernet, over a USB Ethernet, or by Wi-Fi, and then we open a browser and we navigate to Pink 9090. And that will open the Jupyter notebooks, and from within that Jupyter notebooks, you'll see a range of notebooks that come installed with the Pink devices itself. A getting started, a how-to, an explanation. And it's this environment, actually, this web-based environment, that we're going to be using when we come to the next stage of creating our application and creating our prototype, because what we're focusing on now is not the FPGA, the programmable logic design. We know that we can get the camera up and running. We know we can control that camera. What we're looking at now is, does that camera have the correct performance to allow us to implement the algorithms that we want? So does it have the correct pixel depth? Does it have the correct, does it have the correct responsivity, sensitivity? You know, is it suitable for what we want it to do? Has it got the right resolution, bit depth, the whole host of things that come into validating your system? So it allows us to move a step up in that system validation. So if you've never worked with Jupyter before, it's really simple. You know, along the top we have the simple instructions to control and configure the cells. Importantly, we can merge comments and Python, and what happens is within each cell we write the Python that we wish to execute, and then we can run that cell. If that cell fails because we've got a typo or an error in it, we just have to correct that cell and rerun it again, and it keeps running. The previous cells don't need to be rerun. So it really allows for an iterative, error-based, fast-to-fail prototyping development environment that's really quite powerful. What you'll see when it's first run is you'll see that there'll be the brackets with nothing in it, and that'll indicate that the block's never been run before. When there's an asterisk in the cell, it shows that it's currently running, and once it's completed, you'll see a number next to it which shows the number of times that cell's actually been executed. This is what it'll look like in our design when we come to look at it in the next stage. You'll see the different steps for the design. You'll see that we've added some code, we've added some text in there to explain what's going off, and then the actual cell itself. So it's a nice, simple way to set up and to run and to actually begin to document this example. And you can put this straight into your Git source control system. You can put these notes in quite easily. So the other thing to do, obviously, is when you open a notebook up in the Pink environment, the notebook begins to execute, the kernel fires up and begins to execute. So if you click on the running tab, you can see which tabs are running, which notebooks are running. Maybe you've closed a notebook down and you want to close it down and free up a little bandwidth, a little bit more performance. You can do that from the running tab. We can also, if we want to, if we don't like the Jupyter Notebook environment, we can open the Jupyter Labs environment by going to /lab, and this will give you something which looks a little bit more, it's a little bit more customizable, looks a little bit more like a standard integrated development environment that you'll see in software development. And then but it still allows us to do all the same things that you want to do, you know, open notebooks, spin up terminals, and Python shells, and so on. And this brings us to one of the more interesting points as well, the final point. Obviously, when we're working with this, there might be frameworks or packages that we don't have on our Ultra96. So we can open a terminal from Jupyter, and we can go away and we can pull down that information. We can use that terminal to install extra packages and to get us up and running. For instance, if you download my Python overlay for the Ultra96 with this image processing, you will need to install some of the I2C tools, and you can do that by. Okay, so in this second stage, now we've got the Ultra96 all configured and booted with the Pink and connected to it. What we're going to do is we're going to open up this session 2 Jupyter Notebook in the Pink environment, and you'll see this runs across, and you'll see it takes a few minutes for the kernel to start. Once the kernel's started, though, we can start working through the commands that the Python cells. So the first thing we're going to do is we're going to load in the overlay, and then we're going to actually configure the programmable logic with the overlay bit stream. Now, if you want to know what's in the overlay, we can run this command overlay ? And this is going to tell us all the different elements that are in there. So the timing controller for the video output, the interrupt control, the MIPI subsystem, the VDMA, the demosaic, and so on. So this gives us all the information, and it also tells us what the default driver for this is. So you can see here that they've picked up for the pixel pack, it's picked up the video pipeline. For the DMA, it's picked up the VDMA, and for the slow speed AXI light interfaces, it's just picked up the default IP interface. So this gives us this ability to really quickly start working with the IP that we've created in Pink. Now the next step is to run is to progress through this, and we're just going to check the clocks. Now in Pink, we can change the processor to programmable logic clocks as we want. And then we're going to load in the elements that we want. So we're going to load in the Pink library, the Pink video library. We're going to load in the Pink imp. We're going to load in the Pink, the programmable logic library. And then we're going to add in standard Python functions as well. So OpenCV, matplotlib, and SciPy. And then finally, we're going to load in SMBus2. Now, this is going to give us the ability to work with the I2C commands and generate the I2C commands and send the I2C commands down to the imager. So once we've done this, we're going to power on that imager there. And then we're going to run these next few commands down there. And hopefully we'll get an ID of 78 back, which is the ID of the ID of the camera itself. So we know we're talking to the right device, we know we're talking to the right camera, which is important because there is an I2C switch on there. So we do need to make sure that we're going out of the right channel. The next thing to do is actually we need to configure the camera as we want it. So we need to configure the chip to have the correct number of MIPI lines, the correct data rate on the MIPI, and so on, and have all the correct clocking and everything that we need to get it working. So we're going to send that we're going to create a configuration packet there. We're going to check the length of that packet just because I'm curious, and it was 63. And then we're going to send in all those commands. I'm going to write all those commands down to the camera. The next thing we're going to set up in the camera is the auto white balance. So we're going to get that all nicely set up and send the auto white balance down there. We'll check the length again just because I want to know how many commands are in there, which is 19 this time. And we will send down the command again. Finally, we're working in a 720p mode. So what we want to do is set up the 720, get the 720p set up. And this is the packet for this. That contains 38 commands. And we're going to send those 38 commands down. Now the camera's all connected and configured and ready to go. But what isn't is the rest of the configuration, the rest of the pipeline that we need to go from the MIPI input stream and right into the VDMA. We need to configure that pipeline. And to do that, we're going to start with the video demosaic. And in here, we're going to map in the video demosaic to be called demo for demosaic. And then we're going to write to its registers to set the width and height of the image, the Bayer phase, the Bayer pattern of the image, and then we're going to start this running and allow auto rerun. Now, if you're not sure what register addresses these should be, you should be writing to. Then these are available in the product guides of the devices. But this just shows how quickly and easily Pink can be used to get up and running and get that and start working with IP blocks. The next thing we're going to do is a very similar thing with a MIPI. So we're going to map across the MIPI to be named MIPI. And then we're going to read the MIPI status register at channel 60. And we want to see any non-zero value here. This is really important. We just want a non-zero value. Once we've got that, we're going to go away and configure the VDMA. So we're going to configure that for the 720, 1280, 720 lines, 1280 pixels, 24 bits per pixel. And we're going to start the read channel of this to start reading in images from there. If we want to, we can check using the read channel and the read mode to check that we've got it correctly configured. And then finally, what we're going to do is we're going to capture an image for the first time. And hopefully that being able to capture that image, then we can then go forwards and start with the data. So let's take a look at it. We're going to capture an image, and what we're doing there is we're reading a frame buffer from the read channel. We're then converting that into the right color space to work with OpenCV. We're converting an umpire array into the pixels, and then we're plotting the pixels on the screen. So you can see that on the screen there. And what we've captured is actually, I'm going to capture another image. What we've captured actually is a tablet of mine that's actually hosting a public domain web video which shows a number of cars driving about. And that's important because what we want to do now is we want to start developing our application. Now, if we wanted to, we could write our frame out here. We could write the frame to a JPEG if we wanted to. Okay. And then finally, once we've got this, we can output a display on the video. We can turn on the video onto our display port, and we can run this algorithm here. So this is a very simple algorithm that runs round and actually opens up the image processing algorithms on there and does a very simple image tracking application on there, looking at the video that I was saying previously with the cars on it. Now, it's a very simple application. I knocked it up in 5 or 10 minutes just for this example, but it goes to show the importance of what we can do with Pink when we want to start on it, and how we can quickly and easily begin to create applications and prototyping on the real world hardware with the real sensors using high-level frameworks. The next step, obviously, is to then translate what we've learned here into what we want to run accelerate on the hardware, which is what we're going to look at in the next stage when we look at Vitus. But I'll just run quickly through here. One of the important things that we've got in this loop as well, actually, is we can save the video here. So we're going to create a video as well as putting it out onto the TV screen, onto the display. We're going to save a video so as we've got a video that actually works and that looks good. And then we can analyze that to our heart's content as well. We don't have to remember what was going off on there. We can create an image that's doing it. So we're going to create an AVI. We're going to look at this. So we've got the reference frame, the gray screen, the reference frame, which is the first frame that's taken, and then we do any deltas, any differences between the reference frame. So once we've taken that, we convert the reference frame to gray, do a simple blurring on that, and then for the next 500 frames we read the frame, we analyze the frame, we determine what the differences are using simple OpenCV techniques, and we identify those areas on the video, and then we write these to the video frame as well before releasing the video and outputting the video. Now when we run this, what we'll see actually is we will see this output.avi file that's open on our system here, and we can then click on that and we can then download it to wherever we would like on our system. So I'm going to download it here into my downloads directory. And then hopefully I can click on opening it and it will open. If we bring the video across onto the monitor that I'm actually sharing this on, we can pull this back, we can click on go, and you'll see that as the cars go past and it's on a loop, it's tracking and picking them up. It's not perfect because there's a little issue of a remaining frame at the end, but it gives us a good idea of what we can achieve very quickly when we want to use Python and when we want to use this. And this is really, as I say, I'm perhaps labouring the point, but this is really powerful to us and gives us that ability to be able to get our algorithms running quickly, to work out what we want to do most importantly, and then now we're ready to move on to taking a look at Vitus and working out, once we've worked out these algorithms, how we can accelerate them into the hardware. So I think we're going to take a little break now, and then we'll come back for the third session where we will examine how we can create a Vitus application acceleration platform, and we will take a look at how we can what our future steps are there then.
Now in our final session, what we're going to do is we're going to take a look at how we can accelerate what we've been looking at so far. And to do that, we're going to use several features. The first thing, let's just have a quick recap on where we've been and what we've looked at. So in the first session, in session 1, we've looked at how we can control the hardware and demonstrate that the hardware that we've got is actually going to come together and allow us to create something more meaningful. In the second session, we've looked at how we can use Pink to work out what algorithms we actually want with the main sensor. And therefore, now we're in a position that now we know that the hardware works, we've worked out what algorithms we actually want. We're going to go away and we're going to create a platform that's going to allow us to leverage that platform. Okay, so now we understand what we're going to try and do in this session. I need to explain a few of the frameworks and tools that we're going to be using. So we're going to be using Linux to create an embedded Linux solution. We're going to be using Vitus to create the acceleration platform, and Vitus to create the test application that we use. So let's get started. So what is Linux? And essentially, it's a set of open source development command line tools and menus that allow us to build an embedded Linux solution when it's running on an x86 host. So in my example, as you'll see today, I'm going to be because we would need an x86 host running on Linux, I'm going to be using a virtual machine to create this Linux system. And Linux actually, it's really quite simple. There are only 6 commands that are used to create a project to move us all the way through to the end. Now those 6 commands, they do have different options in terms of configuration, creating projects, creating applications, packaging projects to boot, packaging projects to share. But those 6 commands are the basic commands that we'll be using throughout our Linux journey. Okay, so the build system as well. So Linux, it tailors the embedded Linux solution for different Xilinx platforms. So it looks at the Zinc MPSoC, the Zinc, and of course Microblaze. And Pedal Linux tools, you know, because they're open source, we now use the Yocto system since 2016.4. So if you're familiar with using Yocto to build embedded Linux solutions and the different Yocto layers, this is going to seem pretty familiar to you because we've got all that information present and all that build structure there as well. And finally, and this is really important when we move further forwards into the Vitis acceleration and the Vitis application development, but also it's important in Pedal Linux, we include an emulator called QEMU. Now the quick emulator, or QEMU as it's called, allows us to emulate Pedal Linux running on an x86 Linux. And this is really important because it means if we do any kernel work or any application work, we can emulate much faster on the Linux than having to wait for a board to become available. It also opens up some of the development flows that we have when we move further forwards with Vitis and the acceleration flows. So we get everything that we need to get Pedal Linux up and running. So we get the source code, the libraries, the applications, all the Yocto recipes. That all comes as standard with Pedal Linux. It's mostly, you know, it's mostly open source. There's a few exceptions for hardware drivers and such like, but generally it's all open source. And Pedal Linux includes and manages all the kernel source and all the libraries. It allows us to work with that programmable logic. So it generates all elements of the device tree to begin to get us up and running. And it provides all the traditional Linux applications and utilities. Now, because we're using Yocto and it's a standard build system, if we've got anything that's outside the Pedal Linux environment, then we can make use of Yocto to go away and to the Yocto layers to go away and grab it and work with it. So it's really quite a powerful system that we have here to create our embedded Linux solution. So what we get with Pedal Linux is we get everything we need really to go further forward. So we get the bootloader, we get the trusted firmware. So we get the first stage bootloaders, we get the second stage bootloaders, and we get the ARM trust zone as well. So we get everything that we need along with the image, the kernel image, and the configured root file system. We get everything that's needed to create a bootable embedded Linux solution, and also everything that's needed to create a Vitis acceleration platform. So it really, you know, it works well with Vivado hardware designs. Obviously, half these devices is programmable logic, a Linux solution to work with and drive those programmable logic devices. And Pedal Linux does that as part of it. As part of the build, you will see that it configures the device trees for what contents are in the programmable logic. And if necessary, we can then make changes to that program, to those device trees if we need to add in additional information to do further configuration and further system performance. So an example is creating the embedded vision system. We need to do a few more additional steps to get in the device tree for the video for Linux subsystem to be able to understand and work with the image processing pipeline that we've got. And Pedal Linux also, you know, it allows us, it configures the hardware in the programmable logic. You know, we can work with that quite easily. It runs on all the Zinc devices, the Zinc MPSoC, and even Microblaze. The kernel is currently 4.19, and it works really well with either single or multiple CPUs. It gives us everything we need to create the Linux applications, device drivers, and of course there's a lot of configuration files that we can use as well to customize our application. Now, if we need anything further with this, if we want to get started, if we want to understand a little bit more about Pedal Linux, what we can do is we can take a look at User Guide 1144. Now, User Guide 1144 contains pretty much everything that you will ever need to know about Pedal Linux. And it's a really good starting point. It's a really good reference manual. It's something that when I'm developing Pedal Linux solutions for, I've generally got a copy of it open somewhere just so as I can make reference to it and use it. It's a really good, really powerful document. So let's take a look now at what Vitis is. And Vitis is a unified software development environment. And that means that it replaces 3 of the previous tools that came with that were provided by Xilinx. So it replaces the SDK, SDSOC, and SDXL, although it looks very similar to all of them. And again, the reason why it looks similar to all of them is because it's also Eclipse based, and it can be but
But if you want to, then we can integrate it with our own preferred environment, for example, VS Code, or we can run it from the command line. It's really flexible in that respect. And we have two flows. And we've already seen today in the first session, we've already seen one of those flows, because we've seen the embedded flow where we created the embedded where we created the embedded software solution for the bare metal, and we got the device up and running there. We could also use the embedded flow if we wanted to create Peta Linux applications. But today what we're going to be looking at is how we can use that acceleration flow, how we can create an acceleration flow platform. And this is really important, because when we use that acceleration flow, we can use an OpenCL and a Peta Linux operating system to actually move functionality and accelerate performance from being in the processor system to being in the programmable logic. And obviously that gives us significant increases in performance, responsivity, and determinism. And obviously Vitis provides support for both of these flows. So you'll have seen it earlier on, but here's a quick example of what Vitis looks like. You can see up the top where it says DisplayPort and brackets by it out of date, because I've just changed the platform. You can see that it's showing that's the platform. So that's our acceleration platform that we're developing our software on. And then we have the application underneath it. And we can control this, and we can work out what we want in our application. And you'll see in a little while how we can move functions from the PS to the PL. Now the flow is really important. It's really important that we understand this flow. If, like we did in session 1 this morning, we just want to go from Vivado straight into Vitis, what we can do is we can just export the XSA from Xilinx. We can import it into Vitis. We can create a platform in it, and then we can create our Vitis application. Now, in that case, then we're going to be doing an embedded flow type application, because we've not gone via the Peta Linux route, and we've not created the necessary stuff in Peta Linux. If we want to create a Peta Linux solution, either for an embedded solution or for an accelerated application, we export our XSA to Peta Linux. We configure the Peta Linux project, so we generate all the boot systems. We generate but most importantly as well, we also generate a sysroot as well that we can use in our Vitis application. And we take that and then we pass that back. We create this Vitis platform, and in this case we get the choice of whether we want to create an embedded platform or an acceleration platform, because the platform's configured correctly. And then we can go on and we can make our application and create our application and start working with it. Now, one of the interesting things, and one of the things you'll see actually, as we go through this, is to actually create an application in Vitis using the acceleration flow and OpenCL flow. We're obviously moving functionality from the process system to the programmable logic, and that can take considerable time, obviously to implement, because you're going through the stages, you're going through synthesis, place, and route. And that's a little tricky when we don't need to know. So we know what algorithms we want to implement from stage 2. But in stage 3, what we need to do is we need to go away and implement those algorithms using C and OpenCL. And we also then need to, once we've actually worked out what we want to accelerate into the hardware, we also then need to look at the pragmas that are used in that OpenCL code to optimize it for use in the hardware. So unrolling of loops, fracturing of memory, pipelining of functions, data flows, and so on. And to do that and have an iteration time that is an hour between builds or so is obviously not what we want to do. So we have this development flow in Vitis, and this gives us 3 stages, and each stage is really vitally important. So we have that first stage, and that first stage is very similar to what we'll have seen when we used Pink, where we create our software, and we can do software emulation. So we'll create our software, and the idea there is to capture any syntax errors, to find any errors, and verify the functional performance of the system. So is it running the right algorithms? Is the input giving us the right input? Are we getting the right output? Is it doing what we want? Just like we have in the Pink world, it might not then be giving us the performance we want, but we're just proving that it works. The next step is to move to the hardware emulation, because in this step, what we can say is we can tell what functions we want to be accelerated using OpenCL, and we can go away in there, and then we can then put in the necessary pragmas to deal with to allow the parallelization to be implemented. So the loop unrolling, the block fracturing, the pipelining, and the data flow of data. And that we do in the hardware emulation, because that doesn't take as long. It doesn't have as long an iteration loop, but that allows us to run through and optimize the performance in the logic, the interfacing performance, and the resource performance as well, because all this is generally a trade-off between performance and resource. Once we're happy with the system, once we're happy that the performance is good from the hardware emulation, we can take the next step and move on to create the boot files and boot and test on the board. Now, this is why QEMU is so important to us, to enable us to do this emulation flow, because we need to know we can use QEMU for the software emulation and the hardware emulation to help us fine tune our design and get it working. Now, obviously, as well, because we're going to be working with OpenCL, we're going to be working with a lot of libraries. We don't want to have to start writing everything from scratch. We want just like we can in the C++ world, the Python world, we want to be able to leverage standard libraries and use those libraries that are available. And we can do this using the Vitus libraries. So they provide a range of functions, and there's actually, you can kind of group them into two elements. The first element is the common libraries, and these common libraries provide the basic functions which we use across every pretty much application. So examples will be the math.h, DSP libraries, linear algebra libraries. These are the basic building blocks of our algorithms and our systems. But actually, moving on further, we also have a range of domain-specific libraries which are ideally created to help you focus on your value add without having to work on implementing the really low-level detailed algorithms. So there's a lot of domain-specific algorithms that will provide support for security, for vision, for finance, for databases, etc. So for us, obviously, today we're looking at the vision. So the vision libraries are really quite important for creating embedded vision systems. Now, I've mentioned OpenCL a few times, and I think it's important that we understand what OpenCL actually is. Now, it's a framework called Open Computing Language, and the idea is it's an open industry standard, and the idea is to have an industry standard for parallel computing of heterogeneous systems. Now, a heterogeneous system has different elements to it in the different types of processing elements. So it has, for instance, it might have a GPU and a CPU, or a CPU and an FPGA, or a CPU and a DSP. And the idea is we want to be able to pick up create code that without any changes will run quite happily on the CPU, the FPGA, and the DSP. The only thing that changes is the compilation tool used and the performance that you get on the end target, but the code doesn't change. Now, if you're familiar with frameworks such as OpenAMP, this is OpenCL slightly different, because OpenAMP is intended to allow communication between heterogeneous types of processors, say in the Zinc MPSoC between the A53 and the R5, and manage it and communicate it. And it's not designed for really offloading and performance, it's designed for lifecycle management and communication between two processors. OpenCL is really designed to accelerate functions from that A53 into the programmable logic and actually manage and control them and accelerate that data. And what we're seeing with OpenCL actually is we're seeing it being quite popular. We're seeing a lot of market adoption by leading industries, and many companies are developing applications that use OpenCL. Now, the execution platform, the execution model, is actually quite interesting. And it will always have one host, and that host is generally thought of, although it's not going to be in the MPSoC case, obviously, that host is normally thought of as being some sort of x86 based host computer, and then you have a number of OpenCL devices attached to it, often called compute devices, more often called, as I'll be calling them, they're called kernels. Now, what happens here is we create our host code, and our host code we will write using C, C++, or Python or something. And we will make use, on our host code, we will make use of OpenCL APIs to be able to allow us to implement and work with OpenCL. We'll then create our kernel, which are the OpenCL devices. So in our case, we'll create the FPGA design using the OpenCL C language. Now, this is C-like, but it's not exactly C, because there are some limitations that you can't have. There are some capabilities and some really good capabilities and functionalities that C has that don't lend itself to that portability that we want to be able to move across different types of technology without having to modify the source code. So it uses a subset of the C language, and we can use that to actually accelerate. We use this to accelerate functions and algorithms, and it all happens under the control of the host. So the host fires up configures the kernel, sets the kernel up,
and lets it run, and then the host receives the data back. And all it receives is obviously is much higher performance. So when it comes to compiling, you know, the host code, because we're using C or C++, can be compiled using anything such as GCC, G++. In our Xilinx environment, we're going to use XCPP in our compiler. And here, where it's different is the vendor code, because we want to make the code portable across all devices and not make any changes. That's fine. But what does change from target to target to target in the kernel is the compiler, and that's always vendor specific. So in this case, we're going to be using the Vitis compiler, V++, and that's going to compile our OpenCLC into programmable logic gates using high-level synthesis, so that we're in there. So how the MPSoC system works, if you think about the host and the kernel, is the host is the processor system, the kernel is the programmable logic, and we're moving data into and that is our kernel. So we're going to take a look now at how we can create a Vitis acceleration platform. But before we do so, I just want to quickly touch on a few of the resources that have been made available for this session, because there's quite a few. There are 3 detailed Hackster projects looking at each part of this tutorial, so part 1, part 2, part 3. And I've also made available the Vivado projects and Vitis projects for session 1, the Vivado project and a pink overlay for session 2. And then for session 3 coming up, the Vivado project will be available, the Peta Linux BSP that we're going to be creating will be available, and the Vitis acceleration platform will also be available. So now let's take a look at the design, and we'll start taking a look at that design, and we're going to start back again. Okay, so here we have Vivado open, and this is the very similar project to what we had previously. And again, we've just made a few slight iteration changes to the design. The main one is because I want to work with Peta Linux and I want to work with OpenCL. It's easier to use the frame buffer write than it is to use the XDMA. Now, all of the other changes that I'm making actually have been made to work with Peta Linux and to create an image processing platform and to be able to create a Vitis acceleration platform. So the first thing that you'll note, the first major difference in this platform is that the resets on the image processing pipeline. Now, previously, these were all contained by the overall reset for that clock domain using the reset clock. This time, actually, they're all controlled via individual GPIO pins coming from the PSMIO. Now, the reason that we do this is this allows the Video for Linux subsystem to be able to reset elements of it or reset the entire image processing chain without actually resetting the entirety of everything connected to that clock domain. So that's the one change that we've made. So you'll see we've got a couple of slices slicing off from the PSMIO to configure the resets of these as necessary. Now, all of the other changes that we've made have been changes that have been made for Vitis acceleration. And the first thing to do is we're going to need to share some of the PS interfaces. So we need to be able to send out data and control data and configure the IP blocks that are going to be created, so that allow the host to control the kernel in the programmable logic. And that's going to be achieved using the master AXI interface from the process system, because the process system is the transaction initiator. So that is the one that will start that transaction initiation, and it will control the thing. When it comes to receiving data back from the kernel into the process, into the host memory system, the programmable logic will be the initiator. That will be the master. So we'll need to enable some of the slave interfaces as well. Now, really importantly, when we create the slave, when we make the slave interfaces and the master interfaces available, they can't be ones that are currently used in the design at the moment. So we couldn't use this master 0 here because it's connected to the peripheral. If we wanted to be able to connect to this one, we would have to share this peripheral. We would have to, in the Vitis platform, we would have to share this peripheral as opposed to sharing the master port. But I'm going to actually just share unused master and slave ports just to keep this simple. But if you'll notice, and this is really important, I'm not going to be making any changes to the Vivado or to the block diagram to do that. But I'm going to add a few other things in as well into the design. So what I'm going to add in
is to provide clocking for the accelerated kernels. I'm going to put a new clock wizard in there. And within that clock wizard, I'm going to give 4 clock outputs, and I'm going to give the clocks out as 50 meg, 100 meg, 200 meg, and 400 meg. And then for each one of the clocks, I'm going to associate with it a processor reset block, so that it can obviously reset the downstream logic. Now that's going to allow us that with the interfaces and the clocks, obviously that allows us to go away and connect up essentially the kernel that's going to be generated by OpenCL. But what's really needed at that point in time then is to come back and actually enable the kernel to be able to signal to the processing system that it's completed its processing, that it's got data, that it's ready to be read back. And how we do that is we add in this concat block, which is connected to the interrupt port on there. And what you'll notice is I've put a constant on there, and this constant's constantly set to 0. So what will happen is in the actual design, when Vitus goes away to do its compilation, as it needs to use interrupts, it will remove the constant from the interrupt, and it will connect in its own interrupt, connecting into the kernel that's been accelerated so as it can do the signal processing. And that's pretty much all we need to do to make our Vivado design into a Vitus platform. In the block diagram, there's a few other things we need to do within the tool itself. The first thing is we need to enable the platform interfaces. And if you don't have the platform interfaces enabled, what they are is this allows us to where we make the sharing of interfaces to the Vitus compiler and to the V++ compiler. So what we can do is we can see all these interfaces. So for instance, we can see our Zinc processing system, and if you see all the interfaces on there, I've actually enabled on this one, I've enabled the master 1 because we're not using it, and I've enabled the high performance slave 1 and 2 again because they're not using the design. So those ports are available and accessible by the Vitus compiler to connect to its kernels. I've also done the same for the clock. So for the clocking wizard 2, I've enabled all 4 of the clocks and defined one of the clocks as a default. And for the concat block as well, I've not done it, but we can do it now. We can enable the 8 interrupts for the concat block. And if you want to have a view of what's enabled in your design, what interfaces you're sharing, if you click on this block here, it will only show the enabled interfaces. So you can see here, I'm only sharing the 8 enabled interfaces, 8 enabled interrupts, the 4 clocks, and the 3 AXI interfaces. Now at this point, we need to export the XSA. We're ready to export the XSA. Obviously, we need to make sure the platform's validated. And then we can export the XSA. There's a couple of tickle commands that we need to run before that, and they're all included in a script with the downloads. And that will just enable the platform to be configured correctly. So it will tell it whether the platform's running at the edge or the cloud, whether it's intended to be booted off an SD card, etc. And that's what we've used when we went away to create our first application. So from this, what we will get is the XSA file just as normal. Now that XSA file, because it's got an image processing application in there, and that's going to have got some quite tight timing constraints on there, that XSA file is going to include everything needed to allow Vitus to compile and run. So it's going to include all our XDC constraints. So we get everything that's needed to move this forwards and to get the design working as we would hope when we move forward into a Vitus platform. Now, normally when you export this application, when you export this into export the XSA, you don't need to include the bit file because obviously Vitus at a later point in time with its acceleration platform is going to generate that bit file. However, for this example, I included the bit file because we've got that image processing chain, and I want to make sure that my configurations, my settings in PetaLinux, my device tree work in PetaLinux, is going to allow me to boot the PetaLinux image and check that we have the correct image processing chain in line in our Vitus application. So this is what we're gonna do. So I actually built this file and I exported the bit file. And once I've done that, I actually took this into my virtual machine, which is where we started to build PetaLinux. Now this is really important as we start to think about how we want to build our systems and what we want to do. And one of the key things that we want to do is to create our solution for Linux and make sure that we have the image processing chain working correctly. So this is our Vitas workspace, but we're not going to worry about that for the time being. We're going to take a little bit of a look at Linux. Now, Linux is all text-based. It's all based from simple modification of configuration dialog. So let's take a quick look at one. So if we change in in the Linux directory, if we change into the auto session 3 and I run the configuration command linux-config, then this will take a few seconds, but it will open up the main configuration dialog for this system. And all that we need to do is make a few changes to get the system up and running. Is we need to make a few changes to the linux-config, make sure, and in here really we just need to tell it that we're talking to an Ultra96, that we're targeting an Ultra96, and that we're using the standard out, the UART1 as our stood in, stood out. We can see we can get configuration quite easily here. We can change all our systems quite easily. So we can change the component selection, the auto configuration. We can change the hardware setup. So we can change whether we boot from flash or an SD card. We can change our system settings here, as you'll see. So it's a really quite a comprehensive system. We can configure the FPGA manager, the U-boot, the image packing, and even our Yocto settings. I'm going to click on exit for that for the time being, because I've made all the changes that I want to make in that for this application. And this is back to what I was talking about, there being just a set number of Linux commands, but with several options. So I've used the linux-config command there to bring up the overall Linux configuration. If I wanted to configure, say, the kernel or the root file system, and you'll need to configure, if you look at the platforms that I've been talking about, you'll need to configure the platform system, the kernel and the root file system. If you look at the projects that I've created in Hackster, and you can do that using the linux-config -c and then rootfs or kernel to bring up the system that you want to look at. Now, the main thing, obviously, we were talking about this being using Yocto layers and configuration of the platform. So what we can do is we can find our project, and it's under my project here. And what you'll see is pretty much everything is auto-generated for us by the project, apart from what's under the project specification and the meta user layer. So we should only really change things if we want to change recipes, any recipes or anything. We should only change these under the meta user layer. Now, interestingly, under the recipes BSP, under the device tree, under the files, we can if we need to make any device tree changes, we can make these changes to the system user.dtsi. And this is the only device tree changes that we should make, because every other device tree you can find in the Linux project is automatically generated. And what that means is that when it's running, when Linux runs, any changes you've made will be overwritten and flipped away. But what we can see here is we've created quite a comprehensive update to our device tree to define elements of where we want to work with the image processing system. So we've started to create the image processing system with remote endpoints. So to create essentially a device graph that shows how these IP blocks connect and talk to each other. So Video for Linux can pick this up and work for it. You can tell we've told the GPIO resets as well in each one of these, so which ones are associated with the GPIO resets. We've created the video capture element that's necessary. We've defined where the video camera actually is, so the video camera type. And if you look through the project, I'll show you if you look through the Hackster project, I'll show you exactly how to create and enable the support for this in the kernel as well as within the device tree. And then down the very bottom of this, we've put in support for the kernel as well. So you can see here we've got the interrupt support here and everything that's all there. So hopefully in this position now, we're kind of ready to go and build that platform. And when we run and build that platform, what we want to see is we want to be able to see the image processing pipeline is present within our Linux BSP, and that's important because that allows us then to move on to creating that Vitis acceleration platform. So what I'm going to do is I'm just going to quickly open PuTTY up. I've just booted my Ultra96, and hopefully we can log into the project. And if I do a ls of the dev directory, what we'll see is we've picked up this video 0 element. We've got all the elements for the video for Linux system here, and we've also got the necessary media files as well. And if we want to see the configuration and the control of what our image processing pipeline looks like in here, we can do media-ctl-p, and this will bring up the configuration of our image processing system. So you can see we've got the MIPI CSI subsystem, we've got the video demosaic, and we've got the video capture. So this means that we can now be happy that our Linux project that we've built is actually going to work and is going to boot and is going to detect that image processing pipeline. The next stage that we move on to then is creating the Linux, the Vitis acceleration platform. Now this is really quite simple actually. It might look complicated, it might sound complicated, but it's actually really quite simple. And what we need to do is we can create a new, and I have already created one, but we can create a new platform. And when we create a new platform, what we do is we point it to the XSA that we exported from Vivado, because that's the hardware definition. So we point it to the XSA that's been exported from Vivado, and when we get asked which domains we wish to create, we create a Linux domain on the A53 processor. Straightforward so far. And once we've done that, what we can do is we can then just give pointers to we just then give the platform pointers to all the information that we've created as part of that Linux boot application. So we create it to the image.ub, we point it to the boot file, so the first stage bootloader, U-boot, the ARM trusted firmware, the platform management unit firmware, obviously not the bit file because Vitis is going to generate the bit file, but we've also created a sysroot which contains all the information that's going to be in the root file system, and it makes it accessible to the platform as we're working. So if we want to, we can add in additional information for Linux, for QEMU, to get QEMU up and running, so as we can support our software emulation and hardware emulation. In this example, I'm going to skip it, and actually what we're going to do then is we're going to run through and create the platform. Now, what I want to leave you with today, and before we talk to Nick, is I want to leave you with a platform that you can then go away and start working with your image processing applications on it. So the easiest way to do that is we just want to quickly, now we've created the platform, we just want to quickly test it to make sure that it can generate the necessary files and that it will all work together when we boot it. So what we're doing is we're going to just create a simple application this time. We're going to use the built-in vector addition acceleration example just to create an example platform, just to create an example application running on our Vitis acceleration platform, so as we can check that it all works correctly and that there are no issues. And when we do this, when we create this new Vitis acceleration platform, what we will see is we will get a project setting. It's taking a few seconds. We'll get a new project setting, and within this project setting, we'll see here that we're moving the kernel, the kernel vector addition into the programmable, from the processor system into the programmable logic. You'll see that I've set the target for hardware. I've set the optimization for a quick compile time because I just wanted to see it quickly. And if we look at the kernel code, what we'll see within here this code, and we'll see all the pragmas necessary for the interfacing, for the optimization. So this, when you go away and start using this platform to create your own image processing application, this is what you're going to add in your pragmas, your optimizations to give us that performance. So we can then click on this little hammer button here,
which will build the application, and it will create as the SD card. Everything we need to go and put on here will be created on the SD card, and that will, we can then just copy that SD card onto our Ultra96 and boot it, and it should work. So having done this previously and having just put the rebooted my Ultra96, what we can do is we can change first thing we need to do is export the location of the Xilinx XRT, and that's in the system resources area. Then we need to change directory into the SD card because we're working with the SD card, so the files are on the SD card, so we can move into that. And if we ls into that, we can see that we've got everything we need, and we've got our applications in there. So we can quickly run this by running the, if we run the test.exe, run test.exe, and we run the binary container, and if we hit enter, what we'll see is we'll see that run on our device, and we'll see that comes up as test passed. Now what that means is that we've then downloaded the XL bin, is essentially the binary file for the FPGA side of things, for the programmable logic. So what we'll see then is we've created a Vitis application platform. We've demonstrated that it can accelerate applications, albeit a simple application, to the programmable logic, and then we've shown we can run it. What we've run through here is, in session 1, we've demonstrated that you can create a simple platform, you can risk retire the hardware, that you can get something going. In session 2, we've demonstrated that you can use Pink to actually go away and create the algorithms, run the algorithms with the real world sensor very quickly, very easily. And in session 3, what we've done is we've shown you how you can create a pedal Linux image processing chain, and how you can create a Vitis acceleration platform that now you can go forwards with and actually create your own, accelerate your own algorithms into the programmable logic. And really it puts the ball in your court, as to go away and what do you want to go away and create with these tools, with these reference designs that we've created and passed across to you.